Hi group, it's Mrs. Schaus here. We're ready to talk about section 2.2. We're still dealing with functions, but now what we'd like to do is to be able to do some graphing. And in doing that graphing, I want us to think about making tables of values, although that's certainly not the only way that I want us to be able to graph. I want us to use some technology in drawing graphs, and specifically we'll look at some piecewise functions. Remember that I started you out last week in thinking about families of functions because I want us to be able to think about some graphing based on those parent functions and transformations to them, but we're just not quite there yet. So we will begin with something that seems a bit elementary, that is making a table of values as a way to graph. But what I want you folks to think about is, even though it seems sort of elementary, it's a really powerful tool because making a table of values is a way that you could graph or kind of explore behavior with any function. And so it makes it, like I was saying, kind of a powerful tool, really. That's where we're going to begin. So when I look down here at this first problem, we're graphing an absolute value equation, y equals the absolute value of x plus 3. And in thinking about the table of values, sometimes in lower levels of math, you learn things like pick a couple negatives and pick 0 and pick a couple positives or something like that. But as we move a little further along, we realize that that's not always going to be the best case. Sometimes it still will be, but at other times we might kind of miss the mark if we're not careful. We know that the shape of an absolute value curve is a V-shaped, and the parent function kind of would sit right here at with the vertex at the origin, and have this like sort of 45-degree angle here, and then come back this way as well. So if we only picked positive values, we certainly in that case would be kind of misinterpreting perhaps what the graph would look like. Well, in this case, because it's not just the absolute value of x, but there's something else going on inside here, what would be helpful for us is to think about where this graph achieves a 0. So if I put in -3 in place of x here, -3 plus 3, that would give me a 0 output here. So that might be an important piece to look at. I'm going to put that kind of in the middle of my table for my x values, and then I want to pick a couple that sit to the right of that, and then that sit to the left of that. So let me pick like -2 and -1, and -4 and -5. And I think that'll be a pretty good table. Now, just sitting looking at it initially, I don't think that that's probably where you would choose to start your graph. Move this arm down just a little bit. So I'm thinking you might have started with, oops, sorry about the bell. There we go. I'm thinking that you might have started with a couple of small negatives like this. So let's think about plugging those in and see what we get here. If I plug in -2 plus 3, I get 1. If I plug in -1 plus 3, I get 2. Absolute value of that, of course, is 2. So there are a couple of outputs, and I could even plot those points, -2, 1, and -1, positive 2, right there. And then from there, if I had picked 0 in here, and 3 more, that would take me here. And a couple of positive values, let's say 1 and 2. If I put in 1 here, I would get 4 as an output. And if I put 2 in there, I would get 5 as an output right there. And again, what does that look like? It looks like a line. So it's important that we sort of recognize where this is going to change in its, direction, I guess. And that's going to happen where we have this 0 here. So again, 0 as an output here would put us at this point. But now if I plug in -4, for example, -4 plus 3 is -1. The absolute value is +1. And so right here, -4, 1, we see it start to turn back up. That's significant when we're graphing absolute value. -5 plus 3 is -2, but the absolute value of that is +2. And so again, at -5, we'd be here at +2. And that's enough for us to, to see the pattern of what this absolute value graph is doing. Okay. So having this, sort of advanced knowledge of the shape of this curve and its behavior really helped us to make a table that was going to make our graph, more complete. Okay. All right. Let's take a look at another piece. I want you to recall the vertical line test. We talked about that a little bit in class the other day. But the vertical line test basically says that if no vertical line passes through the relation or the graph in more than one point, then the relation is a function. So if I think about I could pick any vertical line that I wanted to and just kind of dropping that vertical line here on my graph, I can tell that any vertical line, no matter where it is, would only touch this in exactly one place. So that tells me that this is a function. But here, it's not that there's one vertical line. There are actually more than one vertical line, but as long as I can find even one where it crosses the graph in more than one place, in this case it happens to be two places, then this is a relation but not a function. This one actually is demonstrating to us here. You can see the line dropping down, and I can tell that it touches 1, 2, 3 different points that are on my curve. So again, I'm going to say that this one is a relation only, or you could say not a function, right? And lastly, this one, I don't know if you guys recognize this one. You will coming up in a month or so when we start getting to some trig pieces here. But at any rate, it has this, just same pattern going on, up and down, up and down. And again, no matter where I drop a vertical line, I'm only going to touch that in at most one place. So this one is also a function. Okay, continuing back with our graphing, I want us to turn for a minute. We're still making tables of values, but we're going to consider the piecewise function. And in section 2.1, you did consider piecewise functions, but you were evaluating them rather than graphing them. What this piecewise function says is y equals x cubed if our inputs are less than or equal to 2. Otherwise, we use the equation y equals x plus 6 when our values of x are greater than 2. So again, in thinking about what we're going to put into the table, 2 is obviously, because of this, a sort of critical point. So we want to make sure that we pick 2 in our table, and then we want to pick some values that are less than that and some ones that are greater than that. Well, thinking about things that are less than 2, let's do 1, 0, and a -1. And then greater than 2, how about 3, 4, and 5? It would be nice if I had some clearly defined axes in here, so let me go ahead and just put some in for us. There we go. All right, let's find these outputs. So if I put in -1, well, I'm going to maybe make a little mark right here. Because what I know is all of these values are less than or equal to 2, so I know that I'm going to use this piece of the description, y equals x cubed. Okay? So -1 cubed, well, that's just -1, right? -1 times -1 times -1. -1 is an output there. 0 cubed is 0. 1 cubed is 1. And 2 cubed, let's see, 2 times 2 is 4, times another 2 is 8 here. Sorry about that light. Here we go. All right, let's plug in the values that are bigger than 2. And remember, if they're greater than 2, we're going to use this other piece of a description of this function. So we're using y equals x plus 6. So 3 plus 6, that gives me an output of 9. 4 plus 6, that's 10. 5 plus 6, that's 11. And we'll plot these points to see what we have. So -1, -1 sits here. 0, 0 sits here. Here's my 1, 1. That looks like a line, but we know y equals x cubed isn't a line, right? How about once we plot the point 2 and then 8? 8 is right there. 2, 8, okay? That might give us a better feel. However, with those few points, unless you have a good feel of what the graph of y equals x cubed looks like, you're going to have a rough time actually sketching that graph. So what might be helpful is if you pick another value maybe that's less than -1, so that we can, kind of look back, and it should be down here, right? Maybe we'll try, I'm going to write it up here, but maybe we'll try a -2 and find that output in just a second. And you might want to, again, depending on your comfort with this, instead of just picking 1 as an input and 2 as an input, maybe you pick like 1.5 and see, kind of where that lands here. If I use -2 as an input and cube that, I get -8. So another point I'm going to add in here is -2, and then I'm going to come down 1, 2, 3, 4, 5, 6, 7, 8, right there. But because I do have a good feel of what an x cubed graph looks like, a cubed function, I'm going to go ahead and fill that part in. Okay. All right, let's take a look at the other points here that I'm going to plot. 3, 9. So I'm going to come over 3 and up, not 8, but 9 right there. 4, 10. So over 4, up 10 here. And over 5, up 11 will sit right here. Now the points that I plotted were right there. And if you look at this, y equals x plus 6, that is a line. So I am graphing part of a line. But there are a couple things I need to consider. First of all, what's happening here? Do those connect or not, essentially, is what I need to know. Well, remember, this is for all x's that are greater than 2. I put in 3, but couldn't I have put in 2.5, which would give me an output of 8.5, right? 8.5. I would be right here. So I'm getting closer to that mark, aren't I? I could have put in 2.1, which would give me 8.1. Like, I'm getting closer and closer to recognizing I'd be at this mark, right? The reason that there's a solid dot here is because of the first piece. If I put in exactly 2 and I cube it, I get an output of 8. So they do actually meet up here. Now the other thing is this says for all values of x that are greater than 2, I stopped here at 5. There should actually be an arrow on the end. And similarly, since it's all x is less than or equal to 2, I should have an arrow on that end as well. Not a linear function for sure. It has these couple of different pieces, but nonetheless, it is a function. It does pass the vertical line test. Okay, take a look at another. Oh, before we get to graphing, we're going to graph some greatest integer functions, but we need to make sense of greatest integer. And I do apologize that the software that I was using did not have a symbol for greatest integer, so this should really be like a double-backed bracket that we're looking at here. So let me just go ahead and kind of change those up, and you can do the same thing within your notes just so we know that we're looking at the symbol that we really mean to be looking at. And we're going to think about defining this function. What does it do to our inputs? So right here, it says the greatest integer that's less than or equal to x. The greatest integer function says as the output, you're going to give the greatest or the biggest integer that's less than or equal to the x itself. So if you're taking the greatest integer of an integer, the output will actually be the number itself, because this says the greatest one that's less than or equal to x. Okay, so that or equal to part kind of kicks in there, right? How about 4.5? We're trying to find the greatest or the biggest integer that's got to be less than this or equal to it. Well, it can't be equal to it because it wouldn't be an integer, right? So the biggest integer then that is less than this would be 4. Okay, for that reason, some folks would call this a rounding down function. How about the greatest integer that's less than or equal to 0.4? Well, again, since 0.4 isn't an integer, it's got to be the greatest or biggest integer that's less than 0.4. The biggest one less than 0.4 is 0. Another thing that sometimes is helpful to folks is to think about a number line and where 0.4 sits. It sits here between 0 and 1, somewhere between 0 and 1. I'm not worried about making that to scale. But what I want you to see is that there are other integers here, -1 and -2, and 2 and 3 and so on. And we want to find the biggest one that is less than this number. So if I'm sitting here, the integers to the right are all larger than. I want the biggest one that sits over here. So the biggest one that's less than this 0.4 would have to be 0. So if it helps you to think about it graphically, by all means do that. Now, The negative ones are where folks really tend to struggle, and that is when I would say it might be really helpful for you to think about making number lines for these. So the negative 0.58, I'm sorry, 5.8 I meant to say, sits between negative 6 and negative 5. Again, I know I didn't draw it to scale. I'm not worried about that. But remember that what you're looking for is the biggest integer that's less than this number. So to be less than it, it actually has to sit to the left of it. Many folks want to call this negative 5, but in fact, it is negative 6. And similarly here, if my negative 2.3 sits between negative 3 and negative 2, not drawn to scale, the greatest integer that's less than this would have to be negative 3. All right, let's think about trying to graph a greatest integer function then. Oops, dropping things. Okay, so in a greatest integer function, in the sense of trying to create this, folks struggle a bit with the table because we have always made tables up to this point where we just pick some values and put in here. Even if we are a little bit strategic about how we pick those values, this is going to look different. And the reason is, let me head back up here again for just a moment. If I were to pick some x's geared around this 4.5 I've got here, instead of 4.5, what if this had said 4.3? What would the greatest integer be then? It would still be 4. What if this was 4.1? The greatest integer of that would still be mapped to 4. Okay, how about if it's 4.75? 4. How about if it's 4.9? 4. Okay, so there's this sort of range, I shouldn't call it a range, but a piece of the domain, maybe I want to say, a chunk of numbers where the output is the same. You know, we know from our work with parent functions that this is a, as it says right here, a step function. We're going to get these little step pieces going on, right, where it increases. And so what we really need to think about is a piece of our domain where our output is all the same. So let's try to make it a little bit more simple on ourselves. And I'll start right here by putting in, what if we put in 0 here for x? Well, 0 plus 1 is 1. That's an integer, so the output for that, the greatest integer that's less than or equal to 1, would be 1. Okay, so I'm wanting to find the other x values where the output would be 1. Well, what if I go a little bit bigger than 0? What if I put in something like 0.25? If I put in 0.25 here, 0.25 plus 1 is 1.25. The greatest integer that's less than or equal to 1.25 is still 1. So I'm wanting to include x's that are 0 or a little bit bigger, but how much bigger? Like, can I put in 0.5 here and still get out an output? I mean, I almost said x, but an output of 1. 0.5 plus 1 is 1.5. The greatest integer less than or equal to that would still be 1. Can I put in 0.75? 1.75 still gets mapped to 1. What if I put in 0.9? 1 plus 0.9, 1.9. Greatest integer that's less than or equal to that is still a 1. So when this actually changes is when I put in 1. Because watch what happens. If I put in 1 here, 1 plus 1 is 2. Now that's an integer. So the greatest integer less than or equal to that would now become a 2. So notice that I don't have equality here. I have equality on this and I'm including the 0. But over here I'm not including the 1 because once I get to that 1, I get an output of 2. And hopefully that helps you to see that for things bigger than 1, like 1.25 and 1.5 and 1.75 and so on, all the way until I get to 2, I would get an output of 2. But once I get to 2, again here, 2 plus 1 would give me 3, so that's going to be the first place where I produce an output of 3. Based on that, let me continue filling in the table here. That'll go all the way over to 3, but not including. And then from 3 to 4, I'll get an output of 4. And from 4 up to, but not including 5, I'll get an output of 5. I can also work backwards to think about some negative values. So it would be -1 to 0, but not including the 0, gives me an output of 0. And from -1 as my right endpoint there, this would be -2. So -2 is less than or equal to x is less than -1 would give me an output of -1. Now let's plot these. And remember, again, they're not points that we're plotting, they're steps that we're plotting. I think in thinking about plotting with steps, sometimes I like to start out with what's happening between 0 and 1. So between 0 and 1, I have an output of 1. So I'm going to come up here. I've got solid dot on this end, hollow dot on this end. So they're very small steps. Maybe I can even, again, bring this down a bit further. Okay? Then let's look between 1 and 2. I'm looking at an output of 2. So it's going to jump up here. And again, hollow dot on that right-hand side. And at this point, you can probably see between 2 and 3, I'm up 3. But you can see the pattern, and you could probably continue on and not really have to worry so much about looking back at the table, right? And then at some point, we just want to put and say dot, dot, dot. Those steps will continue up in that fashion. And now I'd like to think about also putting in some values in this negative direction. And there are the couple that I had actually in my table. But again, now that I know the pattern, I could really put in a few more and then use the whole dot, dot, dot business to indicate those working down towards the left side. All right. But these greatest integer step functions are not always the easiest to interpret. They definitely do take some work on our part. So what tends to happen is that now students say, oh, I think I've got this, and they come over to their next function, which notice is, well, let me put the double back here, but is a greatest integer function, and they want to say, okay, well, I'm going to look between 0 and 1. Well, let's think about that for a minute. If I were to look at between 0 and 1, if I put in 0 here, that would just be 0, so I'd get 1. That would have an output of 1. If I put in 0.1, 2 times 0.1, that's 0.2. 1 plus 0.2, 1.2, would still have an output of 1. If I put in 0.2, that would give me 0.4 here. 1.4 still gets me up to 1. I'm good so far. What if I put in 0.5 here? Or a half, in other words. 0.5 is a half, right? Half of 2 is 1. And 1 plus 1 gives me 2. So at that point, I would now have an output of 2 rather than of 1. So I can't come all the way over to 1. I actually need to come over to 1/2. And sometimes we do a discovery piece on this where I'll ask folks to do a variety of problems, you know, working in groups. But since we're not doing group work currently, I'm going to kind of spill the beans a little and just share. Where does this 1/2, you know, really come from? Well, if you look at the coefficient here, taking the reciprocal of that would give you the 1/2 that I see here. So when you're trying to decide 0 to, you know, to what number initially for this, you know, piece of a domain to look at, you should take the reciprocal of that coefficient, but then do test it and make sure that you agree that that works. All right. So moving on with that, then things between 0 and 1 would give me an output of 2. But once I actually get to the 1 here, once I actually get to the 1, I would get 2 plus 1 more. That would give me 3. So my output would become 3. All right, so this is really 1/2. I don't care if you write 1/2 or if you write 3/2. That's kind of up to you. But I kind of like just leaving it in halves. So I would go from 3/2 to, let's see, that's a span of 1/2. So if I added another 1/2 to that, I would have 4/2, which is really 2, right? And then I would go from 2 to 2.5, which is really 5/2. Those would give me outputs of 4 and 5 respectively, but again, you could check those out. I'm going to try to work back here a little bit. and fill in my 0 and -1. And so, wow, because these pieces are so small, maybe I better make like, I'm going to come out 1, 2, 3, 4. Let me call like 4 of these marks 1. And then 1, 2, 3, 4. That would be 2 and 3. Let's do that. So this will be a -1, -2. I like that because it allows me to see a bigger piece of the step rather than having it look so tiny that we can really barely see it. And then maybe I'll do something similar here. I do need more output, so maybe I'll just, for the Y values, maybe I'll just make 2 of those markings, 1 and 2 and 3, 4, and 5, and I'll do the same thing down below. We'll make that a -1 and a -2. I think that'll give us a little bit better view of what's happening here. All right, so again, I want to start from 0 to 1/2. So from 0 to 1/2 right here, my output is up 1. So I'm going to be here, hollow dot at the end. From 1/2 over to 1, I'm going to be up 2 units. So I'm going to be right here. There goes the light again. Sorry about that. From 1 to 1 1/2, I'm going to be up 3. But once again, at this point now, I see the pattern, and I probably really don't even need to look at the table, right? I could keep going with that pattern. And I could also use the same pattern to work back and fill in these couple of negative pieces as well. Okay, folks, that's all I have for you for now. I'm going to give you some exercises in this section, practicing some of these skills. And of course, reach out to me with questions. We'll talk about the use of our graphing calculator in a different video for time's sake. I don't want this video to be too long, and it's getting to that point. Have a great day, folks. I'll talk to you soon.